Okay, folks, I'm sorry that we have to do this this, and I would have liked to have done a live class, but unfortunately I have a commitment on Monday, so I'm pre-recording this lecture. What we wanted to do is dig a little bit deeper into the chronic penny model and also look at some numerical solutions. Just to remind you now a little bit from the last lecture. Let me share my screen with you. Okay, so this is basically from last time. We have this array of barriers or array of wells, depending on how you want to look at it. So the barriers are of size B and the wells are of size A. And the periodicity of the lattice, therefore, is A plus B. So it repeats after each A plus B. Okay, we said we're going to get exponential type of solutions in here, and we're going to get sinusoidal type solutions here. And then we have to splice them together. And one point that we wanted to pick for splicing is the origin here 0, right? Then things become pretty nice and straightforward. We get this condition A plus B is equal to C plus D. And then we can do the same with the derivative as well at the origin. And we get this. So that's nothing new. We've seen this before. But the next condition then is is going to be these 2 points here. So maybe there was a question that came up on that. So we've sort of stitched together the solution here at the origin, the 2 types of solutions. Now you might have expected or anticipated that we do the same thing here, right? So we have the exponential solution here at x is equal to a, and we have the sinusoidal solution here also at x is equal to a, and we splice them together, and that would give me 2 more equations. Okay, so that would have maybe been my intuitive expectation as well, but what we actually are doing is we're going to do that plus something else. We're going to do that, but now we're also going to bring in the periodicity of the lattice. So we're going to do that in one step. Okay, and so what we said here is we're going to actually splice 2 different locations together, namely minus B and A. And we're going to pick, at minus B, we're going to pick region 2, so the exponential regime, and at point x is equal to a, we're going to pick region 1, so the sinusoidal regime, and we're going to splice those 2 solutions together. So rather than splicing together at the same point x is equal to a, we're going to do one better, okay, and bring in also the periodicity of the lattice. So not just a, but now we're going to look at a and minus b. And so that gives us then the additional 2 equations, 3 and 4. Okay, so that was the idea. But when all is said and done, really what we're going to end up with is this governing equation, P being the barrier strength, alpha here, remember, related to the energy of the solution, okay? Alpha squared being 2m over h bar squared times E. And then K being this arbitrary constant that comes out of the Bloch theorem, and it's just some real number. Okay, so that's the equation we want to satisfy. Okay, and just to remind you here, we said that it may be somewhat difficult to satisfy that equation when P is large. And then when P is equal to when P goes to 0 or is equal to 0, we get no barriers, and we recover the free electron equation. So now the electrons are free again, and therefore the energies are just given by P squared over 2m, right? So the total energy now is P squared over 2m. What does P squared over 2m remind you of? Well, P is equal to mv, right? If you plug that in, you get E is equal to 1/2 mv squared. And that means that E is equal to K, the kinetic energy, right? And so the total energy is equal to the kinetic energy, meaning there isn't any potential energy. That makes sense because we have no more barriers, right? So we are back to the free electron case. All right. Okay, so then we wanted to explore the numerical solutions using Mathematica. So that's what I want to do now. I want to bring up a Mathematica screen. I'm going to do it actually using Wolfram Cloud. Okay, so let me share that screen. Okay, folks, we're back. Sorry for that brief interruption there. So basically, we're looking at wolframcloud.com, and I've uploaded this chronic penny 1.nb, which I'm also going to make available to you on Moodle. So you can do the same thing. You can download it from Moodle and then upload it to the Wolfram Cloud, and then you can open it and play with it. So here, what we have here is first of all, the main equation here, P sinc of x plus cosine of x. So that's sort of the left side of our governing equation. Sinc here, by the way, is sine x over x. Okay, and so in the equation that we had just before, okay, the x wasn't there, but it was alpha, a times alpha, if you remember. Okay, the P is out front, and then sine of a times alpha over a times alpha. So that's going to be just the sinc of a times alpha. And so I'm going to basically use x as a times alpha. Alpha, remember, is basically related to the energy. Okay, so here I'm saying that x is related to the energy of the solution. And I'll say a little bit more about that. But so that's the basic form. I'm also defining here an expression as a function, so a two-variable function of x and p. So I can then plug in values when I refer to EQ. I can plug in values for x and p. And for instance, in the second line now, and remember, you have, when you get to a line like this, you have to, if you want to execute that line, you have to do shift enter, right? That's one of those idiosyncrasies of Mathematica, shift enter. So I did that. And then what we can do is we can just plot that for a particular p. I'm choosing p is equal to 5 here, right? So we're plotting this expression as a function of x, but we're choosing p to be 5, and we're plotting it from minus 1 to 1, no, from minus 15 to 15. Okay. So, and then on top of it, I'm also going to put the +1 and -1 horizontal lines there as well. So let me execute that, shift enter, and I'm gonna get this graph here. Hopefully you'll get something similar on the homework. Okay, so I'm plotting that. So the function is basically has a global maximum here at x is equal to 0. And then it sort of oscillates here. But I've also highlighted, as I said, the horizontal line corresponding to a y value of 1 and a y value of -1. So why did I do that? Why these two lines? Because remember, the left-hand side here, that's only the left-hand side of the governing equation. It has to be equal to cosine of kx, right? And so the cosine of kx has a range between -1 and 1. Okay, and so you can see that we won't find any solutions for x, is equal to 0, for instance. X is equal to 0. This left-hand side is 6. Okay, that kind of does make some sense, right? Because p is 5, the sinc of 0 is 1, so then you have 5 times 1, plus the cosine of 0 is 1. 5 plus 1 is 6. So that it makes sense that it starts here out at 6, but that is much larger than 1, and so there's no way we can find any k such that the cosine of kx is equal to 6. It's just not going to happen. So we're not going to find any solutions there. Matter of fact, we're going to see solutions only starting here, between here and here. That's going to give us one branch of solutions, and then we're going to not see solutions here. Okay, and then we're going to find some more solutions here, no solutions here, some solutions here, and so on. So whatever x values give rise to this left-hand side being between -1 and 1, we would expect to find some solutions. So how does Mathematica find us those solutions? Okay, and so we have two powerful commands at our disposal in Mathematica. And that is, we have the find root equation, or command rather. Okay, so I'm illustrating that here. Find root, okay, here I'm plugging in 2.5 for x and also 2.5 for p. Okay, so if you go back and then I'm going to set that equal to the cosine of k, ka, but the a is 1. The a is just the lowercase a is just a constant, which I'm going to set to 1 here. So cosine of k, okay. And I have to start, when I use the find root command, it does need you to specify an initial guess. And so I set the initial guess to 2 here. And when I do that, it very quickly gives me an answer, namely that k is equal to 1.77488. And so it finds one solution that's near k is equal to 2. There should be another solution, but it doesn't find that. So that's one command that is quite robust, but it does rely on you providing a first guess. The other command that we're going to actually use more often now is the nsolve, the numerical solve. Okay, and so here the format of that of that command is such that, again, like here is the actual equation here in blue, right? The actual equality that you and you want to solve for k. Okay. So the unknown is k, and you want to find a k such that this equation is satisfied here. And here I'm setting p to 5 and x to 3.0. So if you're going to go up here, so this is the graph corresponding to p is equal to 5, and x is 3 in this case. So 1, 2, 3. We're sort of here, okay, at this point, and we want to find a k such that the cosine of k is basically equal to this point here. All right, so when we do that, let me do a shift. Okay, so it takes a little bit longer, and it gives it now in this weird form. Okay, arc cosine and so on. So there you go, but it does come up with two solutions. Okay, plus minus the arc cosine of the equation evaluated for 3 and 5. Okay. Okay, so you can also force it to actually evaluate that. Okay, and when you do that, you get minus 2.42 and 2.42. So these are the two commands I wanted to highlight here. So it's the find root and the end solve. Okay, so now we want to go a little bit further. We'd like to not have to specify x. So here I still have to specify x 3.0, for instance. I'd like to sort of scan through a whole bunch of x values, and for each x value, I'd like it to find the corresponding k value that satisfies the governing equation. So that's what I'd really like to do. I don't want to do that by hand. So what we could, of course, do is, okay, so let's do this. Let's make this 3.1 here and find another solution and so on. For some reason, it wants me to remind it what EQ is. Okay, let's try that. Yeah, so now there's another solution and so on and so forth. But I don't want to do that by hand. I would like it to scan through a whole bunch of values in X. And for each value, I'd like to find a solution K. And so this is this next command here, okay? And this is fairly nestled, but that's the hallmark of Mathematica, is everything is always very nestled. So you see here that we've again used, well, we've used the find root okay, command here. This is very similar to the line above. We've given it a seed of 2. Okay, and then there's this other command that's wrapped around the find root command, that's table. Okay, so table basically runs through a bunch of x values specified here. So we're going to go from x starting at 0 and going up to 10 in steps of 0.025. Okay, so we're going to start at 0. The next value would be 0.025. Next value 0.05 until we reach 10. And we basically repeat this find root command every time, and it tabulates things in a table. So whatever the find root command spits out is the first entry, and then we're going to plot it against x squared. Okay. So why x squared here? Because you might have guessed x here is placeholder for alpha, right? But when you square it, then we get the energy. So I'm going to plot that against the energy. Okay, let's see if this works. Okay. So it does work, and it gives us a whole bunch of error messages up here, but it does spit out this particular graph, which I'm going to make bigger. Okay, so why the error messages? Well, we already speculated that there are many values of x for which there won't be a solution, and it will just then tell us, hey, we couldn't find a solution. So this is not really a bad thing. It's what we expected. We would expect that for a lot of x values, we can't find solutions. So for instance, x is equal to 0. We already said we can't find a solution there, right? Because the cosine of k cannot be 6. So it just tells us that. And so what we see is there are solutions here. And so this here is k, okay, the solution. We're plotting it against the energy here on the vertical axis. Remember, the energy is x squared, and so it goes from 0 to 100 because x ranges from 0 to 10. So the vertical axis is basically an energy axis, and the horizontal axis is basically a k axis. And so each point here is basically one find root command. So far, so good. And so that's what's being plotted here. And you see that we're not getting any solutions. Then we're getting a whole bunch of solutions. Then we're not getting any solutions. Then here's another branch. Okay, no solutions. Here's another branch of solutions, no solutions. Here's another branch. And so that is sort of what we maybe expected here too. We won't find any solutions here. Then there's a branch of solutions, then no solutions, branch of solutions, and so on. Okay. So what we can do here is to play around with the role of P. And so I'm going to also make this available to you, and you can play around with this template here. But what would be nice is to go into this command here and mess around with P. So the second entry is always P, right? So I could set that, for instance, to 0. There are no barriers at all, right? That's the limiting case. And then we get this picture. Okay, so here it's a free electron, basically, right? Because there are no barriers. We've set P to 0, barrier strength, and so we get this interesting sort of zigzag. Okay, but there are always solutions. And what's interesting here is we're plotting them from 0 to pi. Okay, and then of course the cosine is sort of periodic. Okay, and so this second branch could also be flipped over. So flip it over, and we could also, we can kind of see that that would sort of continue this parabola that we are seeing here. Okay, does that make sense? So here we have a sharp turnaround point at pi. Okay, but that is just due to the periodicity of the cosine. We could just keep going after pi, and then these points would be flipped over, and we would continue on this parabolic trajectory. And so that makes sense because the energy is, for a free electron, is just parabolic in K, isn't it? It's h bar squared K squared over 2m. And so we're sort of recovering that here, although we're sort of reflecting back and forth between 0 and pi. Okay. If you want to become even fancier, you can take a look at this command here. It's the manipulate command that's wrapping around everything. Okay, so that's another wrap, and that manipulate command allows you to have a slider where you can adjust P. Okay, so when I execute that, okay, I'm gonna get this window. I wonder if I can make that a little bit bigger for you here. It's having trouble. Yeah, it's having trouble expanding, I believe. Okay, yeah, I can't expand it, but you might be able to see it here. Okay, so up on top is the slider for P, and right now P is at 0. And as we increase P, and you have to give it a moment to update, but now we're sliding, and we're increasing P, and you start seeing, okay, gaps opening up in this picture. Yeah, a big gap opening up here, okay. Gaps opening up as well here. If you want to see a little bit further, you can always plot this from 100 to 150. Okay. We're starting back at P is equal to 0, then I can increase that P, and you see here gaps opening up, although I'm not following in that. Oh, because I would also have to increase the X here somewhat. Okay. Okay. Yes. There we go. And very clearly, we're creating these gaps here where there are no solutions. Okay. Okay, so the upshot then is that we're getting these bands separated by gaps. Okay, bands of solution for different Ks. And then for certain energies, there are just no solutions. And we saw that here. So this is P is equal to 0, but just let's go back to P is equal to 5. Okay, and yeah, so huge, actually, huge gaps between, maybe I should reduce that a little bit. So let's go down to maybe 2, P is equal to 2. Yeah, so then it becomes a little bit more what we saw earlier. Okay, so there are some gaps here between these bands for which, for instance, for an energy of, well, let's expand here a little bit more. One energy of about 5, 10, between 10 and 15 here, there aren't any solutions that we can find for those energies. There are no K values that satisfy the Kronig-Penny equation. And then as we're going past, well, 5, 10, 15, maybe 17, then this other branch picks up, okay, gives us, again, some K values for which there are solutions. And then when we reach an energy of 40, that's when the solutions stop again, no solutions up until 47 or something, okay, and then we pick it up again, and so on. But there are distinct gaps between these energy bands for which solutions exist. That's sort of the big picture, the big lesson here from the Kronig-Penny model is that we're going to get these solutions, but they come in bands of solutions.